Hi, ladies and gents. This time we're going to talk about radiation. There are three ways that heat can be transferred: conduction, convection, and radiation. And this time we're talking about radiation. Radiation is the transfer of heat via infrared radiation or infrared light. Now, there are many different sizes of light wave. There is the visible portion of light that your eye actually is tuned into, kind of like tuning in a radio station. But there are some waves that are longer than what you can see and some that are shorter. All of them are exactly the same type of wave. Some just happen to have very, very short wavelengths like gamma radiation, and some happen to have very long wavelengths like radio waves. Some radio waves are 300 meters long. They're very, very big things. Infrared is right next to visible red, so they're a little bit longer in size than your eye can typically see. Now, all of these different electromagnetic waves have some properties in common. They all travel at the speed of light, which is 3 times 10 to the 8th meters per second, or 186,000 miles per second. They all travel in nice straight lines, and they can travel through empty space. So the advantage with this is if we see any of these lights coming from a particular location in space or with a flashlight or with our eyes, we know that the light has come in a nice straight line. We also use these laser lights for like a laser level because of that straightness. This is the fastest kind of anything that we've ever encountered is light or electromagnetic waves. And this is the only way that we can get heat from our sun. We are not in contact with our sun, and so conduction doesn't work. If the earth was cuddled up close to the sun, we would burn like a little marshmallow. In order for there to be convection, there would have to be a fluid between the sun and the earth, and there is not a fluid that we've actually found of high enough density between the sun and the earth. And so radiation is the form of heat that we get from our star. If you are sitting next to a bonfire or you're sitting next to a fireplace, what warms your body is actually radiation. Now, if you think about this, it's going to be convection is going to make the hot air above this bonfire rise, and cold air is going to rush in to replace it. So this is not making you warm. Conduction would occur if you actually, some poor soul fell into the fire, and that would be very sad, and they'd end up in the emergency room. So how are these people sitting around this bonfire staying nice and warm? It's via infrared radiation. There are invisible rays of a kind of light your eye cannot respond to that are actually given off by this fire, and that's what keeps you warm. If you've ever sat around a bonfire or a fireplace, you know that the front of you has a tendency to get nice and warm, and your back might get cold because it's not facing the fire itself, and these rays or waves travel in nice straight lines. Now, you encounter infrared light in all sorts of different places. If you ever go to a restaurant, very often they're going to have a heat lamp when the server puts food up, and to keep it warm until your companion's meal is ready, there might be a heat lamp, or on a buffet, something like that. If you've ever raised pets, and sometimes you just want to give them a nice little bit of warmth, but you don't want it down in their bedding, you put up a little heat lamp, and a lot of animals really enjoy that extra little bit of heat. Infrared waves themselves are about the size of a pinhead, so they're tiny, tiny little things, but they're still smaller, about the limit of how small we could see it, if we could see one at a time. Reptiles many of them see in the infrared. Now, what's the advantage for a reptile seeing in the infrared? Well, reptiles like eating nice little warm creatures, and so it helps them hunt at night. They're out looking for a warm little snack. So that's an advantage. Your remote control of your television usually has an infrared beam that comes out of it. It's not visible, but these nice straight light beams that you aim at your television set, that gives you a signal that turns the TV on or off. Heat-seeking missiles. Heat-seeking missiles, when they are aiming at an aircraft or any other target, they are going to try and be attracted to the largest source of infrared heat out there. And what's occurring in this picture is this pilot, in an attempt to defend his aircraft, is throwing out some phosphorus flares, producing lots of different heat signatures to hopefully confuse and disorient this little heat-seeking missile. Now, all objects are going to produce some infrared radiation, and it's due to the natural vibration that occurs as objects bump into each other. When objects are cold, they're going to have a low kinetic energy, just vibrating back and forth inside of material. As they get hot, their kinetic energy is going to be greater. They're going to vibrate with more intensity. They're going to bump into each other. These are going to produce a different wavelength of infrared than the colder objects. And there are cameras, thermal imaging cameras, that can actually pick up on those different wavelengths. Thermal imaging is used in so many different applications. This is a thermal image of a home, and it can be used to see where insulation is needed. Obviously, you can see the front of this house is hotter than the neighbors, indicating there's a lot of heat is pouring out of this building, and maybe it needs to be insulated. Fire departments very often are going to have infrared cameras. The firemen cannot see through the smoke, but they want to be able to go in, figure out the source of the fire, put it out without endangering their own lives and saving the homeowners. A lot of industrial applications. This is a food application. All of these hamburger patties need to be at the same temperature. So instead of having a human sitting there with a temperature probe making sure everything is just right, set up a computer, set up an infrared camera, and as long as these are hitting the right temperature, you can automate the system. A lot of health programs are using infrared thermal imaging. You can tell this hoof is hotter than the other hooves of this horse, which might indicate an infection. High blood flow, more heat, and infection. This side of this person, higher heat flow than the other side, maybe that's an indicator of an infection. Military and police also use infrared. Sometimes it's referred to as night vision. And more than anything, it is looking at wavelengths of light the human eye just cannot see. And so they're picking up on the heat signatures given off by people and machines. I love this collection of pictures. Here is a hallway, and here is the same hallway. You can actually see the heat signature of some person's hot little footprints going down the way. After this video, we're going to do another one. We're going to do an example problem with Stefan's law. So this is the equation for radiation. P stands for power. Now that power is going to be the change in energy over the change in time. It's going to be equal to lowercase e, which is the emissivity. No units to that. This is sigma, the Greek letter sigma, and that stands for the Stefan-Boltzmann constant. Capital A is the surface area, and this is temperature in Kelvin raised to the fourth power. This is a cool little law. Now, what does Stefan's law say? Here it is again. Stefan's law says that the rate of radiant heat leaving something depends on surface area. Same thing conduction said. So the more surface area an object has, the faster heat flow. If you have a lot of surface area, the heat's going to leave much more quickly. The other thing Stefan's law says is that because temperature is taken to that fourth power, if you change the temperature between the inside and the outside a little bit, a small change in temperature, big change in rate of heat flow. So if you can turn down your winter thermostat a little bit, you will save a massive amount on your energy bill just with a couple degree change in temperature. And it's due to that fourth power. When we do these problems, couple things to keep in mind. These temperatures must be in Kelvin, and you have to take the inside and outside temperature to the fourth power before you subtract. Last thing we're going to talk about before we do a problem is emissivity. Emissivity is lowercase e. It's a unitless number between 1 and 0. Now, this describes how well an object absorbs or reflects infrared radiation, and this is going to be dependent on color and shine. Now, to give you an idea of what I'm talking about, let's imagine this scenario. You have to cross a road, and it is August, it's the middle of a summer day, and you are barefooted. So the question is, which would you prefer to walk across, black asphalt or gray concrete? Well, your poor little feet are probably going to be less burned to a crisp going across the gray asphalt, gray concrete, than the black asphalt. You know this black surface is going to get really, really hot. That's emissivity. Emissivity is that difference in heat absorption based on color. Now, things with an emissivity of 1 have the name Blackbody radiator, and that term goes back to old studying furnaces done back in the early turn of the century, 1900s. Things with an emissivity of 1 are really good absorbers of heat and really good radiators of heat. Old black stoves tend to be painted flat black, not shiny, but flat, because that makes them really good at giving the heat up to the room, and that's what you want. This is a solar pool heater. The infrared light shines down on this tubing. A pump takes pool water and passes it through these coils back into the pool, and it's black because the black means it's a really good absorber of heat. This is a greenhouse, and in all of these barrels there is water, and they're painted a flat, dull black. So all day, heat, infrared light, warms up the barrels, and they absorb heat. Water has a high specific heat, so it holds a lot of heat. And then all night long, these things that were good absorbers during the day are good radiators at night, and the heat is given back to the plants, and it cuts down on fuel bills. Solar deflectors or collectors have a tendency to have a really high emissivity, be very, very dark, because we want the visible and the infrared to be absorbed. Now, things with an emissivity about 0 are called a perfect reflector. These have a tendency to be white, silver, and shiny. These are good reflectors of heat. There's a reason why people have used white-colored clothing in the summertime, because they're going to be good at reflecting not just visible light, but reflect that infrared. You're going to be cooler out on a summer day in your tennis whites than playing tennis in a black t-shirt and black jeans. Glaciers survive the hot light of the summer because of their white color. That white is going to reflect an awful lot of the infrared, so they don't absorb all the heat, and hence they're going to survive a lot better. This is a solar furnace from France, and that silver shining coating means that they're going to absorb lots of light from the sun, put it into this solar furnace, and they actually use this to melt steel. Pretty fascinating. And you may have heard the old story that white cars in the summertime are cooler than black cars. This is because of emissivity. You can have a huge change in temperature just due to color. All right, that will finish us for this time, and next time we're going to come back and we're going to do a problem. See you then.